Hello guys, I hope you all are doing good. I'm Vaishali Kikan and we are discussing the electronics engineering. Today in this video, we are going to talk about the Zener diode as a shunt regulator, which is the next application of the diode. We were talking about the diode applications. So let's start our discussion with the Zener diode. We have already introduced about the Zener diode's work in the reverse bias condition. It is a very highly doped diode, right? And what we all know about the Zener diode, it is going to regulate the output voltage. So how it is going to regulate the output voltage? By working in the Zener breakdown region, right? So all these things we know. We are going to have the in-depth analysis in this video, right? So now here I told you that it is going to work in the breakdown region. So I hope you have seen the previous video where I talked about the Zener breakdown as well. So let's consider this circuit. Here in the circuit it is going to be used as a voltage regulator. So this is my V in is unregulated voltage. Whenever we have unregulated voltage, there will be always a tendency of the device to get dysfunctioned, or it will be getting harmed due to this unregulated voltage. So we have to avoid this possibility of unregulated voltage and we have to get a regulated voltage at the output. So now V in is the unregulated voltage. It is going to produce a current I, and here we have a resistance which is very important. Without this resistance, we will never be having the regulated voltage if I talk about the Zener diode as a shunt regulator. So this is my Zener diode. This is a symbol of the Zener diode. So the normal diode, here we have the Z sign which represents the Zener, right? So now this is the current I, and here in the Zener diode we have the current flowing, that is IZ, and here at the load we will be current flowing, that is IL. Right, at this load I am going to get the regulated output. So V in is input voltage, which is unregulated output of the rectifier. Now it works on the principle when the Zener diode is operated in the breakdown region or the Zener region. The Zener breakdown region is also known as the Zener region. Voltage across it is substantially constant in a large change of current through it. So even if I change a very large current through the Zener diode, the voltage across it will be substantially constant. If V in is very high, greater than Vz, so Vz is the breakdown voltage and input voltage is greater than Vz, so obviously the diode will be going in the breakdown region. So Zener diode will be working in the breakdown region and it going to maintain the constant load across RL. So the load voltage VL across this RL is going to be constant, right? So now let's apply the KVL over here in the front loop. So here V in will be equal to IR is the first voltage drop plus Vz, right? The voltage drop across the Zener diode. So Vi is equal to IR plus Vz, and from here I can compute I is equal to Vi minus Vz upon R. So this is how I can represent the current. Now VL can be represented as Vz. So over here, if I talk about the VL, right, VL is the voltage across the RL. It is going to be represented as Vz plus IZ/RZ. Now here I consider RZ to be the Zener resistance, which is very small and it can be neglected. So from here I can represent VL to be equal to Vz only, right? So VL is directly equal to Vz, and now from here what is my VL? VL can be represented with the help of Ohm's law. You can represent VL will be equal to IL into RL, right? So now VL is IL/RL, which is equal to Vz. So now the IL can be represented as Vz upon RL, right? So RL is constant, Vz is a constant, so that IL will be a constant. Now if I apply at this node the KCL, so I will be equal to IZ, the current flowing in this direction in this branch, and the current flowing in this branch. So I will be equal to IZ plus IL, right? This is the KCL that we have applied. Now from here you can see if IL is a constant, if I have the change in V in, so I will vary, and due to which IZ is going to vary but IL is going to be constant, and due to which I will be having the changing current flowing across the Vz, right, across the Zener diode, but it is not going to impact the voltage across the load. It would be constant. So Zener is going to maintain a constant voltage across the load. When V in is going to increase, I is going to increase, which means the current through the resistor will become constant. So current through the resistor RL is never going to change. So V out is constant because it is equal to V in minus IR. When V in change, I is changed, so voltage drop across the resistance is going to change. So if I change this V in, what will happen? The voltage drop across this resistance is going to change, but the voltage here would be constant. So this is how the Zener diode is going to maintain a constant voltage. So V in increase, which means I increase, and VR is going to increase. So voltage across the resistors is going to increase in such a way that the voltage across RL remain constant, and reverse is also true. Because the voltage across RL is constant, if VI increase, so VL is going to increase. So now coming to the limitations. We are having several limitations of using the Zener diode as a shunt regulator. The first is low efficiency for heavy load current, because there is a considerable power loss in the resistance, because a very high current will be dropping a very high voltage across the load resistance, right? So there is a power loss which is going to reduce the efficiency. Now, the second limitation is that the output voltage slightly changes due to the Zener impedance, because we neglected the impact of Zener impedance in our calculation, but there will be some impact of the Zener impedance as well. So this is also should be considered while calculating the output. So changes in the load current produces changes in the Zener current. So now I hope you understood all of the things related to the Zener diode as a shunt regulator. If you have any doubt, you can put the doubt in the comment, and I will be trying to resolve your doubt as soon as possible. I hope you like this session. If you like it, please push the like button, subscribe to the channel, share it with your friends, and also give me your feedback. Thank you so much.